cloud. Uh-oh. Welcome everybody to the Murray Amateur Radio Club's in-person meeting. Tonight we're going to talk about amateur radio modes. What the heck is a mode? Too bad it's not a la mode, like ice cream and stuff like that. No, it's going to be ham radio stuff.
You didn't bring the ice cream?
And I didn't bring the ice cream. That's my wife's job. What are you talking about? So we are going to talk about... We're going to talk about radio frequencies. What the heck are they? We're going to talk about bands. We're going to talk about bandwidth. Basically, we're going to talk about the properties of radio frequencies. So it's something you have to know when you're taking the test or when you do stuff with ham radio. And we're going to talk about modes. And we're going to see that all of these things are intertwined into one another. Okay, and here's the deal. If you have a question, anybody, please ask, okay? If I'm using a word that you haven't heard before, please stop me, okay? So let's first of all define what a radio frequency is, and it's always referred to in the ham radio world as RF, radio frequency, right? It's the oscillation rate, oscillation meaning it's going, it's the oscillation rate of an alternating electric current or voltage of a magnetic, electric, or electromagnetic field. That's a fancy way of showing this. Let me bring up my laser pointer. Okay, so here's the antenna on this end, and I'm transmitting, and there are two things that happen with an electromagnetic wave. You have an electric field, that is in blue, and that's going 90 degrees up and down, and then you have a magnetic field which is 90 degrees from the electric field. So you have an electric field and a magnetic field, and then you have the propagation direction. So it's emanating on this particular antenna. It's like a donut, and it goes out. And then you have a wavelength. So each radio frequency has a measurable wavelength, and we're going to talk about that wavelength. As a matter of fact, here is a wave in operation where it's going. Now, of course, this is a slowed down version because the wavelengths that we talk about are in the megahertz, which means millions of times per second. It's oscillating, okay? So this shows phase. Don't worry about that word right now. The ones that I'm concerned about is wavelength, and we're going to talk about modes that are included with that. And so wavelength, which is the 2 meters, and then the frequency. Okay, so those two things, frequency and wavelength, are what I want you to walk away with understanding tonight. So the radio spectrum of frequencies, they're divided into bands. I don't know if you've ever heard of bands before, and they were designed by the ITU, and you can do a Google search for United States frequency allocations, and you'll get this PDF, and it's like a 23 meg file or something. You have to, if you had a huge plotter, that's what this was designed for, because we are talking hundreds and hundreds of frequency divisions, okay? And so the FCC is in charge for the US on how the bands are used, given to us by the International Telecommunications Union, okay? The ITU is the main governing board, and the FCC is the, what do you call it? It's the organization that controls that governs it for the US. Yeah. Okay, and so here's the frequencies and bands that was on that huge poster, and they are divided into bands. And so here's band 3 to 30 hertz. So this is like below hearing, okay, because we hear 60 hertz, and well, some people can't hear 60 hertz, 100 hertz, all the way up to 20,000 hertz if you're a dog. But that's the band, and this is the wavelength for that particular frequency range. And you notice that the ranges are, you start with 3, and then you multiply by 10 and 100 and 1,000, then it keeps on going up, right? So that's how the bands are divided. And as far as ham radio goes, these are the ones that we are concerned about. We are concerned, and actually, does anybody know we just got a new band. It's like 2,200 meters. It's like, holy moly. Say again?
There's 2 new ones.
2 new ones, yeah. So I have to actually modify this so that it includes those. But the ones that we always deal with are high frequency, that's HF. So everybody talks about getting an HF radio. You have to have certain license privileges to talk on most of the HF privileges. Technicians, however, if you do CW, you can get on to the HF bands with CW. There's a portion that you're allowed to do. 10-meter band, you're able to do. If you're a technician, you can run on that as well. But anyway, so we have the VHF, the very high frequency, and the UHF, ultra high frequency. And technicians are able to go from from 50 megahertz all the way up, okay? And I think they're able to go into
Definitely bands about 3 gigs.
I'm sorry?
They're definitely bands about 3 gigs.
Yeah, like the 5.8 gig and all that stuff. So I need to modify this because I think technicians, there is no limit to what technicians can do beyond here. So just because you're a technician, I guess my point is, doesn't mean that you can't enjoy the radio hobby, because there's, oh my goodness, tons of stuff. Yes, Russ?
I was actually a general, but I just barely passed my general when I made my first 10-meter contact. And it was using a speaker wire dipole in my backyard to Easter Island from here in the Salt Lake Valley.
Isn't that crazy?
And it's like, man, techs can get on it. They can do all of this stuff.
Yeah, it's amazing. Okay, so.
When you say text can do all of the, higher gigahertz stuff, and that's where all of the new digital modes and everything are happening. It's all up to the gigahertz range, and you can do all of that, no problem.
Exactly.
That's
Exactly.
all kinds of new technology and everything going on up there.
So I dislike very much when people say, I'm just a technician. That's my point. There's amazing amount of stuff you can do being a technician. Okay, so let's use an example that uses the FM, the audio FM band. It kind of brings it home. Everybody's familiar with turning on the radio, right? And listening to 103.5, your favorite rock station, right? And so what does this mean? The audio FM band is between 88 megahertz and 108 megahertz. What? I just go to channel 5, right? But we refer to the radio station in the frequency that they are transmitting on, right? So you turn your FM dial to 103.5. I have to use 103.5. And what you're really doing is you're listening to a carrier centered at 103.5, which is 103,500,000 hertz. In other words, that radio frequency is oscillating 103,500,000 times every second, okay? Which boggles the mind when you think about it. The signal quality for FM is very, very good. Why? Well, because the mode that's being used is FM. And that's what we're going to talk about tonight. So here is radio station 103.5. That is the frequency. So the question is, what is the wavelength? So all you got to do is either know the wavelength or the frequency to get the other one. It's just a very simple math process. What you do is you take 300, which is the velocity of light, okay, and it's 300 million kilometers per second, right? Meters per second, thank you. And you divide that by the frequency, in this case 103.5, but you notice that 103.5, I'm not putting all the zeros there because we're concatenating. We don't need to put the zeros there to get the wavelength. If we're doing it in meters, or megahertz actually, we're doing it in megahertz, so that's 103.5 megahertz, and this is 300 million, or 300 megahertz if you will. So 300 divided by 103.5 is almost 2.9 meters. So every 2.9 meters, so that's about 6-8 feet, give or take, right? The wavelength is 8 feet, and it's a single wave is 8 feet long, and it's doing that 103 million times per second. Okay, sending it out to the in the air, and it uses a sine wave, and so there you go. And you can do that with any band, any frequency that you want. So let's talk a little bit more about ham radio stuff. If you've been a ham radio operator, you've heard of the 2-meter band and the 70-centimeter band. So what does that really mean? Why do we call it the 2-meter band? Okay, why do we call it the 70-centimeter band? Well, it's the wavelength of the frequency. It's around 2 meters. And I can prove it. So we take 300 divided by, I'm just going to use the 147.16. What's that frequency that we all are using for Murray? Isn't that our Murray assigned?
Oh, see.
Simplex? Yeah. And the length, the wavelength is 2.038 meters. Okay, so, and you do that with any frequency, and it's around 2 meters. Sometimes they're not exactly, but we call it just for ease of use. And I'm going to show an example in the HF, or the high frequency area. So the 40-meter band is a very popular band. It uses, again, I'm talking general class, which means that general class is only able to use the frequencies between 7.175 and 7.3 megahertz, okay? And if you put that in the formula, you can see that the wavelength is 41. That's close enough to 40 meters, okay? Because the 40-meter band goes way below that, and so it actually does hit 40 meters, but just for ease of understanding, we just call it the 40-meter band. There's also the 20-meter band, and put it in the same formula, and there's the 20 meters, around 20 meters. So we have 17 meters, we have 15 meters, we have 12 meters, we have 10 meters, 6 meters, 160 meters, 2,200 meters, 75 and 80 meters, 60 meters, 30 meters. HF is all over the place, right? We have access to all kinds of of bands out there. And any frequency that you pick, you can find out what the wavelength is, right? By the way, that's on the test. So
You can do the reverse too. You need to go from wavelength to frequency.
yeah, that's the first thing I said. You just need to know one or the other, right? And you can figure out the other one. Okay, so let's talk about bandwidth.
If I can, the real easy part is to remember that the 300 is always a constant in that equation.
Speed of light.
And so whichever other one you know, it's either multiply or divide.
Yep, exactly. So
Now it's divided, then, right?
300 divided by, let's work, I don't have my phone with me. Put your phone out there and do 300 divided by
18 meters.
2.01.
0.01.
And I can already tell you, it's going to be 149, yeah. So it's 300 divided by whatever it is you're looking for, okay?
Now let's do 300 divided by, same thing, 14925. 2.01 meters.
Yeah,
So you divide both ways.
yep, exactly,
300 divided by 1 gives you the other.
yep. Okay, we also have a thing called bandwidth. Bandwidth is how wide the frequency that you're transmitting on is, okay? And we're going to discuss why that is important. Well, I'm already showing it here. We have what's called a modulated carrier signal. That modulated carrier signal is the signal that contains whatever entity it's transporting, your voice or a digital ones and zeros, okay? That takes space. We can't use just the center frequency. We have to have a bunch of frequencies on either side to carry that information, okay? And we're going to show how that works. As a matter of fact, on a scope, here we have the center frequency of 433.975 megahertz, and there it is, and you can see that there's more than just the center frequency. There's a ramp up to that and a ramp down. So there's right around here, there's what we call bandwidth. Okay, we're gonna do some more. We're gonna do a close-up look. So here's the bandwidth for this 433.975 megahertz, and this is the bandwidth that it has. Here's one for the 900 megahertz band. This is a 300 kilohertz bandwidth. Every transmission has some type of bandwidth, okay? And so just when you become a general class license, you'll know that anytime you transmit on a frequency, you're dialing on the center carrier, the center frequency. You have to take into account the bandwidth of that frequency you're transmitting on, okay? In other words, if I'm a general class and let's say this is 7.175 megahertz right here. Well, if I were to transmit on that, half of my signal will be going into a band that I am not allowed to transmit on, okay? So I have to move my center frequency over to take into account for that. And all that's because of bandwidth. And you'll learn more about that later on. So we've talked about bandwidth, we've talked about frequency. Let's get into modes, and we're going to see how modes are intertwined into all of this. And it actually has two meanings in ham radio. And we're going to talk about each one of those. It boils down to whether or not we're referring to a type of radio operation that we're using or a type of signal modulation that we're using. So operation mode or modulation mode. And these are words that you may or may not have heard before, certainly operation, but modulation is nothing more than the method of combining your voice onto the carrier, onto the radio frequency so that the radio over there can hear you. That is a modulation. There's different types of modulations, and we're going to talk about that. So let's first of all talk about the operating mode. The operating mode is tells us what type of modulation we're using. So phone is the common term for voice. So anytime I transmit N7XDL, I just use the phone operating mode, okay? HTs, handheld transceivers, these are typically used for phone operations. Not the telephone, but ham radio phone, okay? Let's see, okay. Then we also have digital modes and video modes, and ham radio is able to do those as well. We're going to come back to that. So the concept here is an operating mode may be carried out with one or more individual modulation nodes. So with our phone, which is an operating mode, we're going to learn that we have different ways of putting my voice onto the carrier, onto the radio waves, okay? That is called modulation. And there's different ways of doing that. And we're going to talk about that right now. Speaking of which, there's modulation mode. So the modulation mode refers to the specific method by which information is encoded into the radio emissions. That's a much better way of saying it than what I did. For example, we have FM, frequency modulation, we have amplitude modulation, which is AM, and we also have single sideband modulation, which is SSB. We use SSB for HF. We don't use SSB for UHF, VHF. We use FM and AM for UHF and VHF. Okay. There's also more, but these are the most common ham radio modulation modes that I'm talking about. So these three modulation modes, FM, AM, and SSB, can be used when using the phone operating mode. So operating mode is phone, different ways of modulating that information, and that is the modulation mode. Here's talking about the digital mode. We have PSK31, a lot of different ways of encoding our digital packets, as it were, onto an analog medium, because an RF it's a sine wave. It is not digital, okay? So we have to encode a digital signal onto an analog medium, okay? And so that is how we do that, the modulation mode.
Let me just say, when you're modulating a signal, there are only really three things you can do. You have your carrier wave floating through space. You can either change the frequency up, or down. You can make it more powerful, less powerful, or you can move it forwards and backwards. Those are all the only three things you're ever doing to that carrier. And all these modes are just different combinations.
Different ways of doing it. Exactly.
Make it faster, slower, bigger, smaller, or forward or backwards.
And we're going to actually get into that. Then the other modulation mode is continuous wave, or CW. CW is Morse code, okay, and we're going to talk about that a little bit later on. So here's the comparisons with the operating mode phone. There's others, but these are the common ones for ham radio. There's digital. Again, this is just a short list. There's lots of modulation modes for digital. There's video, and CW is CW. It has its own thing. So let's talk about more specific ham radio modes. And this is exactly what Justin says. We have radio waves, right? These electromagnetic waves. There's only so much you can do with them. You can change the amplitude, you can change the frequency, and you can change the phase, okay? And it's how you do that is where the art comes in, right? So a mode is nothing more than changing a way changing any one of those properties of the radio wave. That's called modulation. Modulating signals can either be analog or digital, okay? And we do this all the time. You don't even know you're doing it. There's two main analog modes, and this is what the UHF and VHF radios will use. We have amplitude modulation called AM, okay? Aircraft uses amplitude modulation. As a matter of fact, when you buy a ham radio, some ham radios are unable to receive aircraft signals because they are not built with AM modulation capabilities, okay? You have to have AM built into it. Generally, that's not what they market. This is an AM radio. No, what they market is this will receive aircraft communication. And if that's the case, you know that it can do AM stuff. And then we have angle modulation, which has part of that frequency modulation, okay? So many people refer to the ham radio modes as AM and FM, but technically, FM is part of the angle modulation mode. And then we have HF. So again, like I already said, a transceiver produces a carrier wave at this frequency of transmission. There's my example, 14.258 megahertz. Voice is superimposed on the carrier wave and alters its shape by changing the amplitude or height of the wave. So HF, we're going to be using a form of AM, amplitude modulation, and we're going to use a special kind of amplitude modulation, and we're going to see that. So here's what's actually happened. Here's our voice. Has anybody seen their voice on an oscilloscope? Okay, how it's really quick and there's squiggly lines. This is, that's what that is. You have the carrier signal. So my radio is producing 14.258 million cycles per second. What the radio does, what the modulation does, it encodes this onto the carrier, and so this is your AM signal. You can see that it follows the same waveform as your voice, and it's the carrier signal, the frequency doesn't change, but it's the amplitude that changes. As a matter of fact, with HF radio, I can be transmitting. I have a 100-watt radio over there, and when I transmit on HF, I'm using 0 watts, even though I have my transmitter set to 100 watts. The only time wattage starts coming out is when it hears I talk into the microphone, okay? And then you can see the power go from 100 watts down to 25 watts, down to 3 watts, down to 75. It just does it really quick, okay? That's because of this right here. It's the amplitude that changes, and this represents 100 watts, this represents 20 watts, okay? So power is also involved with amplitude modulation, which is reason why it doesn't sound as good as FM transmissions, because FM does completely something different. We're going to talk about that. Okay, so amplitude modulation produces the output signal, and it does it twice the maximum frequency of the original baseband signal. So what does that mean? Okay, we have this center carrier frequency, 14, whatever that example was. And we have a lower side band part of the signal and an upper side band. And together, this is called AM. a full AM modulation. It uses both sides. But as we'll find, that is very inefficient, okay? Our 100 watts is being divided across the entire spectrum here. Notice the bandwidth here. So there's quite a bit of a bandwidth cost for that. So what we do is we use single sideband modulation. And it's just like it sounds. We have the upper or lower sideband of a carrier that is amplitude modulated, okay? And here's...
That's the positive, the negative, when you do the offset?
Yeah, no. The offset is still using FM transmissions, so it's completely different.
That's a frequency adjustment, right?
Okay, so the offset is the repeater is listening on one frequency and you're listening on another frequency, so you need an offset. Repeaters use two separate frequencies.
Not which side of the...
It's not which side of the carrier you're on. Yep. So, to save power, the carrier in one of the sidebands is eliminated. So if I have 100 watts, actually this next thing will show us here. This is 100 watts right here. Not a very good signal. There's no telling, well, actually, the AM broadcast uses this right here. That's why AM broadcasting uses hundreds of thousands of watts, because they're using both sides of the carrier, okay? But with ham radio, we use either upper sideband or lower sideband. And as you can see here, my 100 watts here, if I were to put it on just one of the sides, I'm able to boost that signal tremendously, okay? So that's why we put that's why we use single sideband, so that we can go further with the same amount of power, okay? And it's not really going further, it's putting more oomph into the signal that helps it go further, okay? There's lots of things that enable the signal to determine how many FARs we get, right? Because I can talk to Japan on 5 watts using CW. I can also talk to Japan using 1500 watts using single sideband. So a lot of things that we need to talk about before we get into that. Okay, so we have AM, which is amplitude modulation. Then now we have FM, and typically that's used for the VHF and UHF radios. So let's go ahead and talk about this. Here we have the modulating, here's the carrier, so 144.45 megahertz, okay? And here's the modulating wave. This is our voice. When we modulate our wave onto the carrier, this is what it looks like. You can see that the frequency changes, okay? The amplitude is the same. Okay, that is why FM transmissions always sound better, because we're pushing out 5 watts all the time, whether you're whispering or you're yelling, it doesn't matter. It is 5 watts coming out of the radio, okay? That's why we like to do 10 meters on FM, because of that very reason right there. So comparing frequency modulation to single sideband, the question is, why is the music that you listen to on FM radio sound so much better than what you listen to on the AM band?
You're probably listening to part of the...
I'm sorry?
You're probably listening to part of the bandwidth.
I mean, yes, but there's more to it. So what does FM mean?
Frequency modulation.
Frequency modulation. That's exactly 103.5 FM, 103.5 frequency modulated carrier. You can say it that way. We're using a huge amount of bandwidth, and we haven't talked about that yet, versus AM, which still can use a wide bandwidth, but the power is spread out. And so you get much more fidelity on the FM. And there's actually more to it than that.
Like it's a more efficient use of the spectrum, so for the same power, you can get more information, which means better quality audio into your same chunk of the spectrum.
Part of it is because the frequency is higher, so the bandwidth is greater. You can carry more information because of the higher frequency.
Right. And there's one more piece that there's a slide that will talk about it, so we're gonna hit it.
Shouldn't you also compare kind of like to a phonograph versus the distortion? I can't think of the word right now, but in AM, it's more of a fuzzy phonograph versus FM, it's got the more, what's the word I'm looking for? Resolution. Is it,
Yeah.
can you kind of look at it that way? Is it
Yeah.
The frequency versus the ampacity, you know.
If I were to put it into a JPEG or a picture, that might be a great way to describe it. Yeah, yeah. Higher resolution on the FM, lower resolution, but you get a much wider picture on the AM side.
This is funny.
It's not carrying I'm not sure it's not carrying as much information. It's how the information is carried. That's the difference between FM and AM. Anyway, hold on to that. We're going to, I'm sorry?
Well, here's the answer right here.
Here-
Just wait it again.
Yes. So, FM requires a much broader bandwidth than SSB. FM is 12 to 15 kilohertz versus SSB's 2.5 kilohertz. So it's up to 6 times the bandwidth difference, which means that if you have a huge swath of bandwidth, that's a lot of information that can be carried on that, right? And so that's why the fidelity is so good on FM versus single sideband.
And bandwidth is again the peak on the one side down to the peak on the other side of the line.
It's the other one. So,
Oh, the vertical versus the width.
yes, yeah,
Horizontal.
it's how long the,
I thought that was a meter.
well, okay, so it is similar to wavelength, okay, because it uses the X axis, right? And it requires a certain amount of the X axis, that's called bandwidth. So you have the center carrier, let's call the center carrier 100 hertz, 100 megahertz, okay? And if I'm using AM, then I'm going to use 300 kilohertz on one side of that and 300 kilohertz on the other side of that, total 600 kilohertz plus the center carrier, okay?
That's the very first picture you showed where it was the wave, the
Yeah.
horizontal wave versus the vertical wave.
The vertical wave is nothing more than showing the location of the carrier wave, the target frequency, 103.5. But with 103.5, you have 6 kilohertz of bandwidth. Actually, you have 12 kilohertz of bandwidth versus on a single sideband transmission, you have the center. Actually, we don't even use the center carrier. It is right next to the center carrier. And if it's upper sideband or lower sideband, you're using only 2.5 kilohertz versus 12 kilohertz. Huge difference.
But going back to what Travis said, if you increase your amplitude, like with AM, you will use more bandwidth. Right? If you have a very low, volume, so to speak, you're not getting as much bandwidth as if you've got power and volume.
The bandwidth's the same.
I think they'll be good.
On that
Remember,
one.
on AM.
Oh, yeah.
Because bandwidth
I'm-
change if you transmit louder?
No.
The same, it's totally the same.
The,
Like,
when you look at it on the scope, you know, you have that ramp up and ramp down, right? On SSB or even AM, when you're talking real slow, that kind of narrows down. So I guess it does adjust it, only because I think it's logarithmic, ultimately in the chips, and I don't know how they do it, but they do it, right? But you'll notice that the bandwidth is still there, it just, at the very edges, it just goes down, just because it's the modulation that goes down, right? The bandwidth is the same though, it just goes down to nothing.
It's because if you're not moving that wave around as much, you don't need as many other frequencies. I
True.
mean, if I understand it, I could be wrong, but that's what I'm understanding. If the waves are barely deviating from the carrier, the number of frequencies you need to produce that don't deviate very much from the carrier. But if you
We'll put that on the side for now.
I guess what I'm saying is I think what Travis said was kind of correct. Like the bandwidth isn't exactly that, but I think what he said is correct, that the higher your peaks, the more bandwidth it is.
Yeah, and I'm gonna say, I don't think so.
Okay. But fair enough, we can.
But I've been wrong before, damn it. So, okay, so let's continue on here. And I'm just gonna go over these. This talks about things that we don't need to worry about. It's on it'll be on our website. You can go ahead and read that. That gets more in depth into the FM modulation, why it's much better. So, why is single sideband preferred for HF? Well, because we're able to concentrate all of our power to one section of the band. So here's actually a question. Which of the following is an advantage when using single sideband as compared to other analog voice modes on the HF amateur band? The question is very high fidelity voice modulation, less bandwidth used and higher power efficiency, ease of tuning on receive and immunity to impulse noise, or less subject to static crashes, atmospheric. What do you think the answer is? B? Well, it turns out you're correct. So less bandwidth used and higher power efficiency. So instead of taking that 100 watts for the entire bandwidth, we're bringing it into either the upper sideband or the lower sideband. And as a matter of fact, here is the bandwidth to each of the modes. SSB is 2500 to 3000 hertz, AM is 6000, FM is 5,000 to 15,000 hertz. So quite a bit difference. Here's, you can look at this at your leisure. With AM, this talks about the entire frequency on a center carrier frequency. This is using 14.25. This is why I say that when you're running HF, you need to know if you're running upper sideband or lower sideband and how close to the band edge you are, because you have to take this into account. And that's also true with single sideband. You still have to know, just because I'm transmitting at 14.25, the outer end is 14.350, I think, for 20 meters. So if I am transmitting it, if I tune my radio to 14.350, guess what I'm doing? I'm transmitting 3 kilohertz out of my band, which means I'm transmitting illegally. Okay, so I have to take this into account. Don't have to worry about that until you study for your general class. And then we have continuous wave. This is the very last thing that we have to talk about. Continuous wave is It turns the transmission on or off using Morse code. The wave is continuous, and here's what it looks like. We have a constant wave. Anytime I do a DIT, it keeps that frequency in use, as it were, and then when I release the key, there's nothing there, and then the DAW. And as you can see that there's a 3-to-1 ratio between the DITs and the DAWs, and that's all I'm going to talk about with that. So let's talk about the bandwidth of CW. This is amazing. Bandwidth for CW is less than 10 hertz, not kilohertz, hertz. 10 hertz to 300 hertz. Holy moly, that is nothing. And when you look at that and compare it to a SSB voice channel, 2.8 kilohertz voice channel, well, this is why you can put hundreds of CW contacts, conversations, in the same bandwidth as a single voice communication, okay? And I say hundreds, but that's not true. But typically it's about 300 hertz is the bandwidth of a CW signal, and you can just put tons of them in there. So even though it looks like when you go down to the CW part of each band, doesn't look like there's a whole lot of band space for that, well, there really is, because the bandwidth of CW is so small. So when you put it on a scope, you see that you can put a lot in there. As a matter of fact, if you look at the power density of CW, let's compare CW to SSB. And we're doing it based on power density, or the bandwidth versus the power that we're using. So with CW, I'm doing 1 watt per hertz. Okay, this is assuming I'm using a 5 CW, I'm using 5 watts. And so the bandwidth is 100 hertz. So my power density is 1 watt per hertz. For single sideband, I'm going to use 100 watts. That's a typical 100 watt HF radio. The power density is 0.05 watts per hertz. Okay, so what does that mean? Well, 5 watts of CW is equivalent to 100 watts single sideband. This is, in my mind, one of the reasons why you don't need much on CW to be able to talk around the world. Okay, you only need a 1 watt radio. A 5 watt radio is called a QRP. QRP is a code in the ham radio world that means low power. And low power is defined as 5 watts or below. So anytime that if you're listening to an HF radio and you have somebody calling, this is N7XDL QRP, everybody wants to get a hold of him because he's running 5 watts or less. And people like to see how well they're able to contact that guy. Anyway, that's continuous wave. And one thing that I have here, and Sam, you're not going to be able to see this. Who else is on the line here? MB. Is this Mike? Who's MB? Could you unmute on the Zoom, MB? Okay, I guess not. Okay. So this is actually the end of the presentation. Does anybody have any questions before we go over to the bench here? We're going to talk about CW and kind of get your, maybe exposed for the first time, just to see what's possible. I'm certainly not someone who knows CW, I'm learning it. But I did make my paddle, and I want to show you how easy it is to do. But we're going to talk about the continuous wave, the CW. But before we do that, any questions before I stop the recording? Okay, I'm going to stop the recording. Let's see, stop recording. Yes, I am